Okay, so now I'm going to go and carry on and talk about anisotropy, mechanical anisotropy. And now it's going to be specifically about zirconium alloys because zirconium, as I explained earlier, has an anisotropic crystal structure. The crystal structure is shown here, and on it I've marked the most close-packed planes. And as I said before, for zirconium, because it has a C/A less than ideal, it's a C/A about 1.59 as opposed to 1.63 with magnesium, which is close to ideal. That's what you get when you have close packing of spheres. I think 1.683 is the actual number for close packing of spheres. But because zirconium has a smaller C/A ratio, that means that the most close packed planes are these prism 1 planes, as opposed to the basal ones, which were normal. And what that means is that you tend to get more preferential slip on these planes as opposed to any other planes. But there's an additional complication with zirconium because you have the possibilities of numerous slip systems which have dislocations of different type that participate in the deformation. So what I'm going to be talking about is the effect of mechanical anisotropy, and that comes about A, because of the crystal itself, but also because of how all of the grains, the agglomeration of crystals, are gathered together in a particular material or component. And the case study, if you like, I'm going to be telling you about is the case of calandria tubes, which is also for fuel sheathing. Same thing, it's the same texture roughly. And what we're talking about is the fact that many of the grains have this unique C-axis in the hexagonal unit cell, have the unique C-axis in the radial direction of the tube. This is represented on a pole figure, basal pole figure like this, and you see that the intensity, the profiles, sorry, not the profiles, the contours which dictate the probability of finding a basal pole increase as we go towards the radial direction. So that means that most of the grains are oriented with the C-axis up in this radial direction, up and down. And this imparts some anisotropy. And when it comes to localization, changes in the anisotropy because of fabrication can dictate where a component will fail, which is the weakest part, depending on the stress state. It's kind of interwoven, a little bit complicated, but not too bad. So let's move on. So this is a busy slide, but I can step you through it. When we talk about yielding of a material, which is a parameter, a mechanical property parameter, which is often very valuable and needed. We need to know it. When it comes to isotropic materials, many of you are probably familiar with the von Mises yield criteria, in which case the yield stress, or if you like, the von Mises stress, which would be a yield stress in a uniaxial test. If it was a uniaxial test, this would be the yield stress. But the von Mises stress, some value here of a stress value is there is a single value which is dictated by the stress in each of 3 directions, sigma 1, sigma 2, and sigma 3, shown here with these axes here relative to a particular component. There's a given value of stress, or the von Mises stress, where the material will yield. So it's a criterion. As I say, if this was a uniaxial stress state and we only had sigma 1, we'd have sigma 1 squared and minus sigma 1 squared, which is 2 sigma 1 and equals 2 sigma 1 squared. So the von Mises stress in that case would be the tensile yield stress. A little bit more complicated when you get to zirconium alloys, because it's not so much a von Mises stress as an energy criteria. And Hill from the University of Bristol, he devised or reasoned that the point at which the material will yield, especially for an anisotropic material, is dictated by how much work you put in. What is the how much energy you have to input to get to a certain point when the material will plastically deform. So it is a kind of a stress squared relationship, and I don't know, but I'm guessing that's because if you think about it, energy is, if you have a stress against strain graph, energy is half stress times strain in an elastic material, roughly. So given that the strain is it is basically the stress derived from the stress is basically E, the modulus times the elastic strain. So given that the elastic strain is the modulus times the stress, then given that, the modulus times the stress is modulus times the strain, sorry about that, then one can see that in deriving the energy, which is half stress times strain, if we represent the strain now as in terms of a stress, it would be the stress divided by the modulus, by the Young's modulus. In that case, the energy input is basically in terms of a stress squared. So you have this stress squared criteria, and Hill had a kind of similar kind of expression. It's not called a von Mises stress. He would do it. It would be in basically, you could either call it K, single K, or K squared. It doesn't really matter. But at some point at which the energy input leads to yielding. Now, the neat thing about these criteria, and I'm not sure which came first, the chicken or the egg kind of thing, but it turns out that the Hill's yield criteria, and the same applies to von Mises as well, is actually the characteristic, is the characteristic equation of the compliance tensor. So the compliance tensor basically relates the strain rate to the stress state using this tensor expression, and in this case in terms of the Hill's anisotropy coefficient. Now Hill, when he derived this expression in his book in 1953 or something, when did he do it? 1954. It's on the bottom there. When Hill derived this expression, he never once mentioned tensors. But it turns out that if you approach the problem from different directions, Hill did it in terms of work done and energies, just like Eshelby would have done, and Peach Caller for slip and stuff like that. If you approach it from a tensor point of view perspective, you get the same answer. So if you come at it thinking, well, we have to consider that to describe the deformation of any material, plastic deformation, while conserving volume, you can describe the deformation just simply empirically using this matrix or this tensor. And you can relate it through some scaling factor here. Sometimes people call that a compliance, but it's a factor, and you can get to the same answer here just based on a tensor consideration. So just simply wanting to describe the strain rate in 3 different directions, one can relate that to the stress by this, what amounts to a set of balance equations. And the balance here is volume. The volume has to be conserved. And, if you can solve this expression up here in terms of FG and H, or for certain FG and H, and for those conditions, if we plot the solution of this equation for different values of K in stress space, in this case it's axial and transverse stress, we can plot a series of, plot a surface, and this, because we're typically looking at it in 2D, that's the easiest way to plot it. This is a slice through, in this case, in the plane normal to the radial direction of the tube. So we're talking about a plane stress condition, pressurized tube. We assume that the stress normal to the surface is negligible, 0, and then we only have to concern ourselves with the axial and transverse stress. So we're taking a slice through a yield surface in the plane of the tube, in the radial transverse plane, and we're looking at the relationship between the point of yielding and the stress state given by various stress loci. The beauty of looking at it in terms of tensors is that when you consider it in terms of tensors, it becomes much more simple, because we know from tensor physics that the radius normal property is what gives you these strain rates. So the vector, which is normal to the surface where the stress locus intersects the surface, that vector, the normal to that surface, the direction of that vector is the same as whatever the ratio of these strain rates. So although the magnitude might vary depending on what this factor is, the direction of the strain, or the components of the difference of these in the strain rates in different directions, can be deduced simply from the radius normal property. So let me go into that a little bit more, give you a bit more detail, and explain to you why this is important when it comes to localization. So let's consider a closed-end biaxial creep capsule where the hoop stress is double. The hoop stress in the transverse direction is double the axial stress. This is the stress locus. And then this blue line here is for an isotropic material. It's a cut through the yield surface in the axial transverse plane. And this point here, where it cuts the axial longitudinal axis, this would represent the uniaxial axial yield stress. And this point here is the transverse yield stress. So for an isotropic material, of course, they're equal, 2.5, 2.5. And this is just scaled in nominal units, so don't worry about it. So one of the things that you should realize, and probably do realize anyway, is that if you have a biaxial, closed-end biaxial capsule, and you follow the stress locus up to the point where it intersects an isotropic material, the strain from that isotropic material is perpendicular to the surface, which in this case is vertical. So what that means is there's no axial strain rate. The axial strain rate is 0. However, if we have consider another case, let's say we have an anisotropic material, in this case something which is harder in the radial direction. This would be the case for that high radial basal texture. So the transverse and the actual yield stresses are, if we have fewer basal poles in those directions, it's going to be softer in those directions. And we do a uniaxial test and follow this stress locus where it intersects the yield surface. For a transverse tensile specimen, we see what the transverse strain rate is compared to the actual strain rate. Anyway, it's an easy way to once you've figured out what F, G, and H applies to your material, whether it's isotropic or anisotropic or how it's anisotropic, then you can deduce how it's going to strain for a given stress. So to explain this better, the best thing is to show you by example. And so I'm going to do that. And the example I'm going to choose is a calandria tube in a CANDU reactor. So this is a fuel channel, one of 380 in a CANDU reactor typically. And what you have here is a pressure tube which contains the fuel and the coolant, and it's hot. And we have a moderator outside here which is cool. And the way to preserve your heat in the fuel channel so it can get to the heat exchangers and generate your power is that you have these spaces here and they maintain an insulating gas gap. And the way to do that is have an annular coaxial tube, which is called the calandria tube, and that's attached to the structure here at the end. So the calandria tube is, in fact, if it was pressurized, it would be a closed end, fixed end, sorry, it would be fixed end, whereas the pressure tube, because it's got these closures here, it's like a closed end biaxial pressurized capsule. So and this just shows you how the temperature and the flux varies along the fuel channel. So by way of introduction, why did we become interested in calandria tubes? Well, it started off many years ago, back in 1983, just before I joined AECL. There was a pressure tube failure, pressure tube G16 in the Pickering 2 reactor, and that occurred because the pressure tube sagged, made contact. It was a zircaloid tube and had a high hydrogen pickup, and then you got some hydride blister formation, and the thing eventually failed and cracked. I mean, it catastrophically cracked along the tube, and you had a loss of coolant accident. Now, 2 years or 3 years later, there was another LOCA, but for a different reason. This was a manufacturing defect in a pressure tube. And what happened, I should have mentioned that in that case, it was okay because the LOCA, the coolant, even though it was pressurized, was contained by the calandria tube. The calandria tube in the P2G16 case held the system pressure. In this instance, in 1986, the pressure tube went bang again for a different reason, but it's also hydride related. But this time the calandria tube failed, and the calandria tube failed by what's a water hammer, and it failed along the seam, along the weld. So the calandria tubes are typically manufactured by taking some strip, rolling it around, and then seam welding it. And the reason it failed in this case, this latter case in 1986, is that the tube had actually been reduced in thickness to 1.4 millimeters, as opposed to the earlier reactor, which was 1.6 millimeters. And that 0.2 millimeters made all the difference to being able to hold the pressure. These things happen in reactor development, and particularly in the CANDU reactor, because neutron economy is so important, because they only run on natural uranium. And that was one of the outcomes, is that the calandria tube failed on the LOCA. So there was a program initiated at that time, a lot of concerns about welded tubes. So the program was initiated to make a seamless calandria tube, and we could get away from the weld. So the seam welded fabrication was concerned over burst strength in the event of a pressure tube failure. So a new design called for a seamless calandria tube, but also one which had a high radial or transverse texture that I make it strong, even stronger. So my branch at Chalk River, where I worked and I was the manager, we had responsibility for the burst test facility, and so we would get samples and have to test them, test the properties. And this is an example of a seam welded tube that had failed in a burst test in the facility. So this is a fixed end burst test, and what you can see is that when it's tested to failure, the split on the tube occurs down the weld. Now, for the same material, if one looks in the main body of the tube, and you take a tensile specimen just to check on the properties, the interesting thing is that it fails in the main body, not in the weld. So in the one instance, for a biaxial stress condition, the failure happens in the weld. For a uniaxial stress condition, the failure happens in the main body. So I think many people had forgotten this over the years. I mean, this is would have been standard stuff for engineers back in the 50s and 60s, but sometimes people need to be reminded about what this means and how to deduce how a material is going to fail. And I can demonstrate that with this diagram. So what I've got here is the solution to the Hill's yield criterion, and I've taken textures, 3 different textures, one which is representative of the main body of the calandria tube, and because it has a high radial basal texture, that means it's softer than the isotropic material in the axial directions or the transverse direction. So the yield strength in uniaxially is going to be softer for this blue one, the main body, as you'll see. And then we got the weld, which is an anisotropic material, and there for the closed end test here, you could see it intersects the yield surface at the point where the radius normal would be perpendicular, which would be, vertical, no axial strain. And for a seamless tube, which is what we were testing for, the seamless tube has, in this case, a higher basal transverse texture, stronger in the basal direction. And again, that's good because the intercept here, if it was a closed end, not so much if it was a fixed end, not so much in a closed end. We want the fixed end condition, so the darker dashed line is what's relevant for us. So let's see what happens when we do the 2 types of tests that I just described. So if we take a uniaxial test, we increase the stress in a tensile specimen until it intersects the yield surface. So if this tensile specimen contains the main body and the weld, which one fails first? Well, it's the main body, as we saw. and that's because that intersects then the yield surface at this point. Now we take a fixed end biaxial test and we increase the stress or increase the pressure. What happens? Well, we hit the weld first before we hit the main body, and it would be even worse for the seamless tube, which is highly textured, of course. So that's it in a nutshell. This is why we get that failure in the weld, and that's why the reason I wanted to mention it is because it in effect is a way of describing the anisotropy. It's, sorry, not anisotropy, localization. In this case, this is localization, failure along a weld, simply because of the stress state and simply because of the anisotropy of the material.